Well, now we have the paragraph for questions 11 to 13. Let's read the paragraph. It says, liquid of density rho is filled into a cylindrical container of radius r and height h. The container is placed on a platform at height h by 2 above the ground. A small circular hole of radius r is punctured on the wall and near the bottom of container. Now this is the arrangement shown. Question 11 says, just after the hole is punctured, velocity of efflux is this much, velocity of efflux is this much, acceleration of top layer is this much, and acceleration of top layer is this much. Okay, so the options are about the velocity of efflux and acceleration of top layer. Now the speed of efflux expression is simply V is equal to root 2g. Let's say if the height of the liquid column above the hole is capital H, then this is the expression. Now in this particular case, capital H will be simply small h. So that means velocity of efflux will be root 2g to small h, which is option A, matching with option A. Option A is correct, option B is incorrect. Let's now evaluate acceleration of top layer. Now for this we can apply the equation of continuity, equate the volume flow rate. So that means we have, if this height is, let's say h, and of course the hole has been made here, we can see that capital A into minus dH by dt, this will be equal to the volume flow rate, minus sign because h is decreasing with time, is equal to area of the hole, which is pi small r square, because the radius is smaller, into the speed of efflux, which is 2g h. Well, here h has been taken as a variable, so let's proceed with this. Now we know capital A is pi into capital R square, so this gives us fact that minus dH by dt is equal to R square by capital R square into root 2g h. Let's differentiate it again, and that gives us minus d2h by dt square. This is equal to small r square by capital R square into root 2g into d by dt of root h, which is 1 by 2 root h dh by dt. We already have the expression for dh by dt. So expression for d2h by dt square then is coming out to be small r square by capital R square into root 2g into 1 by 2 root h into dh by dt, and we can put a minus sign, we shift here, so minus dh by dt we can replace. Minus dh by dt is actually equal to small r square by capital R square into again root 2gh in the numerator, right? Let's simplify this expression. This is coming out to be equal to small r to the power 4 by capital R to the power 4, and this is simply g. So this will be the acceleration of the top layer, and if you look at the options, well, this is matching with option C. So option C is correct for question 11, option D is incorrect. Let's go to the next question now. Question 12, based on same paragraph, says, as the liquid drains out, velocity of efflux decreases continuously. Velocity of efflux first decreases, then increases. C says range of efflux liquid first increases, then decreases, and option D says range of efflux liquid decreases continuously. We know, as per the question, the hole has been made here. So the height of liquid is initially h and it continuously decreases. That means the speed v will continuously decrease, okay, which is nothing but root 2gh, and the value of h is continuously decreasing. So that means option A will be correct and option B will be incorrect. Now, well, the range of the liquid is clearly proportional to the speed of efflux, because the time of descent will be same in all the cases, and time of descent multiplied by the speed of efflux will give us the range. Since the speed of efflux is decreasing continuously, the range will also decrease continuously. Pretty easy, isn't it? Let's go to the next question now. Question 13 says, let H1 be the liquid level when horizontal range of efflux liquid on ground is maximum and equal to R. Then, well, so when the horizontal range is maximum, then H1 is clearly equal to H. We just discussed in the previous question. H1 will be H for horizontal range to be maximum, right? For range to be maximum. Now in this case, the speed of efflux will be root 2gh, and the time of descent, to get time of descent we can write the equation half g t square is equal to h by 2, which gives us the value of t as under root h by g. And so horizontal range in that case is root 2gh into root h by g, and this is simply h root 2, and so r is root 2h is also correct, and h1 equal to h is also correct. The other two options are incorrect. Let's see the next paragraph now. Well, the paragraph for next two questions are here. It says two strings of linear mass density mu1 and mu2 are knotted together at x equal to 0 and stressed to tension T. A sine wave A0 sine omega 1t minus k1x in the string of density mu1 reaches the junction between the two strings, at which it is partly transmitted into the string of density mu2 and partly reflected. Let these waves be A1 sine omega 2t minus k1x and A2 sine k1x plus omega 1t respectively. Based on the given information, answer the following questions. A0 is positive. If there is no energy loss at junction, then okay, so the junction is at x equal to 0, and so we have this is x equal to 0. This medium has linear mass density mu1. This medium has linear mass density mu2. And as per the question, here wave number is k1 and here it is k2. Remember, speed is omega by k. Now this is the situation. Now if displacement of a particle is represented by y, then for the sake of continuity, what we have is y due to incident pulse or incident wave plus y due to reflected wave at x equal to 0, right? Just to the left of the boundary, it has to be equal to y due to the transmitted wave. Okay. Now it has been given to us that the reflected wave has amplitude A2 and the transmitted wave has amplitude A1. Also, if mu1 is greater than mu2, then that means the speed in medium 1 is less than speed in medium 2, and that being the case, there is no phase change due to reflection. Okay, so which means we can write here then that A0 plus A2 is actually equal to A1. This will be correct if mu1 is greater than mu2. As I said, we have to consider continuity of displacement of a particle at the junction and also consider the fact that there is no phase change due to reflection, because the reflection is happening at a boundary with a medium where the speed of the wave is greater than the speed in the first medium. So A will be correct, and which clearly means that B is incorrect. Let's look at option C and D now. It says what happens if mu1 is less than mu2? Well, if mu1 is less than mu2, then that means due to reflection there is a phase change. This inversion of pulse due to the reflection, and if that is the case, then A2 will be negative. Okay, so that means D is also correct, C will be then incorrect. So that means for question 14, A and D are the correct options. Let's go on to the next question now. Question 15 says if mu2 is 4 mu1, then option A says omega 1 equals omega 2, option B says omega 1 equals 2 omega 2. Well, we know that the angular frequency or the frequency of the wave is determined by the source, not by the medium. So the angular frequency will not change. In both the media, angular frequency is going to be same, which clearly means that omega 1 equals omega 2. It is not affected by the linear density of the media. So that means A is correct and B is incorrect. Now we know that speed V is under root T by mu. So this means V2 by V1 is equal to under root of mu1 by mu2. Now if I put the value as given, mu2 as 4 mu1, so this is 1 by 2. Now this is also equal to, because speed V is omega by k, so omega is same for the two media, that means it is equal to K1 by K2, and which means that K2 is equal to 2K1 is also correct. So that means C is correct and D is incorrect. Let's go to the next question now.